In this particular problem, we are going to model the radiation modes of heat transfer using Ansys Workbench. So here we take a heating coil and we try to pass electricity through this coil. And due to the resistance present in this coil, heat is being generated. And due to the vacuum present inside this particular glass bulb, this mode of heat transfer will be through radiation. So we are going to stimulate the internal heat generation, and also we are going to put up radiation boundary conditions, and we are going to test out this heat transfer using Ansys Workbench.
Now we have opened Ansys Workbench and drag this steady state thermal and place it on project schematic. And now go to engineering data, select engineering data sources, go to thermal materials library here and select this tungsten. Select it and add it to my analysis and close this engineering data. Now right click on the geometry, import and select this particular heating coil. And then double click on the model cell in order to open Ansys Mechanical. Here the mode of heat transfer is through radiation. So we need to give emissivity as well as ambient temperature as an input. Now go to this heating coil in geometry and change the material from structural steel to tungsten. And then right click on the steady state thermal, insert and select this internal heat generation option. Select the total body because internal heat generation is a property of the total body and press apply. Now give the magnitude of this internal heat generation, which is around 0.02 watt per mm cube. Just right click, insert, select radiation. As we know, radiation boundary condition is a surface property. Now select all the external surfaces, but for that purpose select this particular surface first and select this extend to limit so that this particular surface along this total path will be selected. Now press apply and give the emissivity value is 0.25 and give the ambient temperature of 30 degrees centigrade. Now right click on the solution and solve it. Then right click, insert, go to thermal, select temperature, again right click, insert, go to thermal and this time select total heat flux. And now evaluate both of these results. Right now select the temperature and we can see the temperature distribution inside the coil. And now select total heat flux and now we can visualize the total heat flux present in the coil. We can also see these results in the form of vector arrows. Now all the values are being displayed with this particular lines or arrows which show the magnitude as well as the direction. The heat is coming out of this particular coil, that's why it is showing the direction that the heat is coming out of this top of the coil. We can also change the size of these arrows by using the slider, and we can also change the display of the arrows by using these options. And this particular option, the amount of heat generation that we have applied to the coil, it is 0.02 watt per meter cube. And for finding out the volume we can go to the geometry, and here in the properties we can see the volume and it is 15,978 mm cube. So what happens, 15,978 into 0.02 will lead you around 324 or say 320.5 watts of energy. So for that right click, insert, go to probe tube and select the reaction probe. So here the radiation is the boundary condition that I have selected and evaluate this result. See here the value is equivalent to minus 324 watts, which is very near to our analytical calculation. So this is how we can also confirm that our analysis is somewhat good.